James, I remember when we were in Switzerland, we stopped in a little shop and you looked at a Rolex Milgauss. Did you ever get it?
I still pine for it. So you remember the motivation behind it.
I'd
So
love to
I
hear.
try to yeah, so I've had a career where I like to like, capture specific moments in the career and then have these objects, and I love watches, use these objects as a way to tell a narrative to my son about my career as a scientist. I'm a scientist. And so one of the things that the first thing I have that is really, the beginning of this as a narrative is my Omega Speedmaster. I try to acquire the watches as a function of some milestone in my professional life. This corresponds to 2004. I began my first, what I would say, like real professional, not truly, but real professional job, which was a tenure track position at Vanderbilt University. So I got this many years later, well after I actually left Vanderbilt, but it's like the beginning. Like this is where I see myself really beginning as a professional scientist. Yes, I did things before then. I was, got an advanced degree. I taught high school and things like that. But for me, this was like the initiation, like the initial. Okay, fast forward to the Milgauss. I'm looking for a specific date. So, 2010 or a 2011 Milgauss, because it signifies the next milestone for me, which was in 2010, earning tenure in physics, or in 2011, which is where when I earned tenure in chemistry. And so if I can identify either one of those dates, specifically in a Milgauss, because again, Milgausses were designed for scientists who worked at CERN, because many of the equipment and the environment associated with working at CERN, the big particle smasher, affected watches because of ambient magnetic fields. And so the Milgauss is specifically designed to resist some of the changes in the proper cadence of the ticking, if you will, of a watch because of the presence of ferromagnetic materials in the watch. And so when the Milgauss tried to remove all of that, so there was no ferromagnetic material that would be adversely affected by random magnetic fields in CERN. And so even though I'm not a particle physicist, I'm a physicist, my background and my research activities were in magnetic and magneto-optical properties of nanomaterials, hence the connection to the Milgauss. So I
Can you
haven't gotten
unpack
it
that just
yet.
a little bit?
Sure, I could say. So when I joined Vanderbilt, I had to propose what research I would like to explore and what avenues of research activity I would like to push the frontiers of to really set myself apart as a leader in a particular field. One of the areas that I chose was an area called rare earth nanomaterials. And so every few years, rare earths become like the hottest thing that people talk about. Not as much in the science of rare earths, although that's very steady, very strong. It's in the public consciousness because of their use, rare earth materials, their use in a variety of things, from magnets to renewable energy devices, energy storage, batteries, and things like that. And the thing is that one part of the world has a preponderance of the refinement of these materials from raw ore state into a usable material state. So there are geopolitics that get involved, most certainly. And so my interest were in magnetic properties, trying to understand not only what gives rise to the magnetic properties of these really amazing materials, and I'll explain where they come from and how
Mhm.
you might be able to recognize them in a second, the magnetic properties, but what might turn them on and off as a function of the size of the material itself. And so that's one of the tenets of my area of nanoscience. It was nanoparticles. Nanoparticles are the types of materials that if you change the size of them, you can actually change the physical properties or the chemical properties of them.
And how do you
Imagine
change the
having
size of them? Is it heat, cooling, speed?
Good question. So I made or synthesized is the technical term, synthesized these by taking chemicals, large quantities of chemicals, and causing those chemicals to react with each other. Those reactions turned those chemicals, sometimes they were in liquid form, sometimes they were in a mixture of solid and liquid form. Those reactions started to create really tiny crystals. And if you can control the temperature, the environmental temperature, the pressure, and the right amounts of these special chemicals, you can control the size extremely well. You can also control the shape extremely well. And so the areas where I contributed to the science were coupled between finding very amazing control over the size and shape, and that size and shape correlating to really interesting physical properties, both magnetic and optical properties. And so the size I'm talking about, if you're not a nanoscientist, is often hard to fathom. And so I'm going to use an analogy that often gives people the aha moment. And so you are fortunate, Mark, because you have hair on your head, and I do not. It's a testament of how many times I've done this analogy. I've plucked a hair from my head and stretched it out. So if you did that, let's say figuratively, and stretched it in front of yourself like this, and then you took an extremely sharp knife and cut it, that hair along its length, roughly 10,000 times in equally sized chunks. One of those cuts would be roughly a nanometer. And so the technical equivalent is 1 times 10 to the negative 9, or nanometers. So not a thousandth, which is 1 times 10 to the 3, negative 3, or 1 millionth, which is 1 times 10 to the negative 6, but a billionth, which is 1 times 10 to the negative 9. So it's a billionth of a meter. And we were just, before we started this conversation, we were talking about our kids. And so my 5-year-old son is about a meter tall. And so if you cut that meter tall, which is roughly here, maybe up to your hip, and you cut it into a billion with a B, equally sized chunks or sections. One of those is roughly a nanometer. Okay, so I was looking at things that were anywhere between one nanometer, and around three of those in size. Extremely small. One last analogy to help kind of conceptualize this. How many atoms does that correspond to? That also gives you a sense, because atoms are really small. So some of the materials that we were synthesizing controllably, repeatedly controllably, had around 100 atoms in it. Just think about that. Tiny, tiny, tiny atoms crumpled together in a regular array that's called a crystal or a lattice. We were making those and trying to understand how their magnetic properties changed if you added just say 50 more atoms or 10 more atoms. But the insight is that the rare earths that I was looking at from every textbook known to man up until the point I started studying them stated that if you change the size of these nanomaterials, the properties shouldn't change at all. And there's something intrinsic to the atom itself, the rare earth atom itself, that made that so. But what we found was that at these extremely small sizes, there were surface effects that caused the individual atoms to behave very differently. And so some of the work that we did, along with graduate students and postdocs that were working with me, revealed this for one of the first times. And so that was why I was really excited about pursuing that work.
What's the application for this?
So historically, some of the materials that we were investigating, which are called phosphors, they're not magnets, they're phosphors, are used in everything from television screens to X-ray detection systems to even light emitting devices like lights that are overhead or lights that are in a flashlight or even a laser. I was pursuing interests that would make really lightweight, really efficient TV screens and other display devices. And so this gives you also roughly a time in the world where we were transitioning from cathode ray tube screens or CRT screens into, the best when I started this work were plasma screens. You may recall plasma, like these really heavy but extremely intensely bright, really rich color type of TV screens. And so I was thinking about using some of my really tiny nanomaterials for those types of screens.
You mentioned that this is rare earth. Are we the lucky ones here geographically? Does everybody have access to this? Is there a market for this?
So yes, no, and maybe so. So it's well known in the rare earth community that some of the largest deposits that exist on Earth exist in China, in a specific region of China called Inner Mongolia. I've actually been fortunate enough to visit Inner Mongolia earlier in my life. There are other deposits around the country. There's a well-known region in the United States, Mountain Pass in western United States, that also has a non-trivial, a very good amount of rare earths. But one of the challenges with rare earths in general is that it's very labor intensive. It's very resource intensive to transfer the raw material, the raw ore that you dig up into usable materials, usable things that can go into magnets or TVs or other types of devices.
So it's not really cost effective for startups to pursue or raise capital on.
There's an ebb and flow over the last 20 some years where new innovations, new scarcity of finished article material or finished material. That's the stuff that you get after all of the mining that occurs, all of the processing that occurs, that it becomes even more cost effective to do the mining in some of these locations around the world. The markets drive it. And so that's evolved over time in ways that make places like Mountain Pass, places in South America, places in Australia, as well as others, Europe even, but smaller in Europe, much more viable to invest in the raw mineral mining as well as the processing, or the finishing. It's still most cost effective in China for a variety of reasons that I'd rather not get into because of the geopolitics, labor costs, environmental costs, things like that. I try to stay out of politics. So, but there are definitely initiatives, I should say, that are occurring in the U.S. and that are exploring opportunities from U.S. domestic rare earth ore sources.
Interesting. One part of your training is nanomaterials. What is your other training in? Is it black holes? Is it intuition? Is it alternate universes?
Well, I'm a proponent of people pursuing STEM careers, very much so. Not because I want the world to be populated only by scientists, engineers, technologists, and mathematicians, but I want people to at least be exposed to those disciplines and those academic pursuits, regardless of college, high school, grade school, etc., because many of those disciplines train you how to think in a certain way, how to use critical thinking to analyze a problem, diagnose what might be possible solutions, and to come about a certain way to come to a resolution, be it an answer, be it another question, be it the decision that there may not be a solution for the problem that you're trying to address. And so for me, that is actually part of who I am. It's something that I only later in my life, after being a college professor, did I realize that that was part of my fabric. Back in college and back at even high school, when I wasn't sure if I was going to be an English major or an art historian or a radiologist.
Yeah, you flipped a
Uh,
coin, right?
yeah, I'll tell that story. It's people don't believe it, but it is totally true. I didn't know what I wanted to pursue. So trying to identify like who you are, how you go about waking up every day and engaging, I find to be useful. And so okay, so you brought up the coin flip. So in college, so there's a pre-story to it that makes it make more sense. So in college, I went to Amherst College in Massachusetts, a small liberal arts college. And I had the intent to either major in physics, math, computer science, or English. That was my intent going in. It was going to be one of those four. And after my first year, I realized I didn't really like computer science. I think it was largely what was offered as introductory computer science classes that just turned me off. And so I whittled it down to three. After the completion of the first year and a half, I was math or physics.
And did you always know that you were good with numbers?
I don't know if I am good at numbers, honestly. I found that I was good at things that I liked. And so I pursued things that I liked.
Okay, so
But I don't know.
you have physicist, math, computer science, which is heavy math, and then English. 3/4 is math, and then your Wharton grad, which is math. So I would argue that you are pretty good with numbers or pretty good with math. What makes you think you're not? What got you to that point of, I understand that you wanted to pursue something that you love. Was math just super easy and you loved the component of it?
Well, the math that I had certainly in high school and grade school, I found to be easy. But it doesn't mean that math was easy. The math that I had was easy. And so it set me up. Later on, I found math to be more challenging, but it always felt like it was part of how I thought about things. And so even though if it became more challenging, linear algebra at some stage, group theory at another stage, vector analysis, different sorts calculus, I felt like it was part of how I thought about things. So even if I found it challenging, it didn't just deter me. It didn't discourage me. But back to the coin flip, because all of this is related. It's all related. Second semester of sophomore year, I had to take one more class to be fully registered or fully enrolled because you had to have
Full-time credit,
a
whatever it may
certain
be.
full-time credits. Exactly. That's exactly it. And because I was heading toward a physics major, I ultimately could only find one class in the entire offerings of Amherst College that fit into my schedule. And it was a senior level seminar on Chinese art. And so when I saw that, it was the only class I could take. It was just one of these, okay, that's fine. I'll sign up for it. Then I read the fine print. Fine print said that you had to have taken so many art history classes and you had to apply. On top of having a multitude of art history classes, you had to apply to get into the seminar. And so I had neither of those at hand. I had never taken an art history class. I didn't even know really how to apply. So I went to the professor and begged, like, look, I need to be full time. Please let me in your class. Unbeknownst to me, the enrollment requirement for the course to be taught was five, and he had only four students who had signed up for it. So he needed me as much as I needed him. He gave me a little bit of a hard time. We're now friends. He's a fantastic guy. And he said, okay, I'll let you in, but you got to be careful. You're going to have to learn a lot about the history of art to keep up. And so I remember first day walking into the classroom. Classroom was completely pitch black and had a curtain uh, at the front door. So you had to walk yourself through a curtain to get into the classroom. And before me was a replica, but a fully authentic replica of Fan Quan, the artist, Travelers Among Mountains and Streams.
Chris,
It had,
can you pull this up? I want to see
yeah,
this
pull
image,
this up.
please.
This is one of the first moments that I knew my life had changed. Truly, like it was one of those profound moments. I still get worked up by it because it totally changed my life. That moment walking in and seeing that that piece of art. From the time, oh, sorry, I'm getting teary because it really is a profound moment. I remember it like it was a couple minutes ago. So yeah, there it is. So
Okay.
after that moment, I started taking history of art classes. And by the end of my time, from second semester sophomore year to the time that I graduated, I ended up being one class shy of a double major of physics and the history of art. And so that same professor, a gentleman named Sam Morse, fantastic guy, he knew that I became not only interested in the history of art, that I became really conflicted because I didn't know what to do. I'd committed to physics, but I also had these heartstrings pulling on me that the history of art might actually be what I should pursue. And so he did me one of the biggest favors ever. He called someone he knew at the Smithsonian and he got me an internship at the Smithsonian in the Freer and Sackler art galleries, which are the Asian art galleries of the Smithsonian. And I spent some time doing two different things. One was working with the curatorial staff, the art historians of the Freer and Sackler galleries, to understand how professional art historians actually operate. The second part of it was that I worked with an area of the museum called conservational science. Conservational science is the scientific study of art. And so I spent my internship doing both, a little bit of curatorial work and then a little bit of conservational science. Fast forward, my first two publications, the first two things that were published out in the world that have my name on them, one is a research publication on the scientific study of art coming from the Smithsonian. And the other one is my name just in small letters in a catalog of an exhibit that was showcased in late 1996 from my work in the curatorial department. And so fast forward to the actual coin flip. Because I didn't know what I wanted to do, history of art, maybe conservational science, maybe physics, I took time off and ended up becoming a high school teacher because I was truly conflicted. I had an amazing time. I learned how to teach during that time. I was fortunate to have amazing master teachers that helped me along my way on the pedagogy, the science and practice of teaching, which still I use today, those learnings. But at some point I decided, okay, I want to pursue an advanced degree and I don't know what it's going to be. And so to my nature, I let the universe decide. And so I took a coin and said, okay, I'm going to flip this coin. Heads, it's going to be the pursuit of the history of art. Tails, it's going to be some type of science. And I literally flipped a coin because I had done some pre-work before, so I had applied to graduate programs and I had offers and I just had to decide.
So I have to ask you, according to physics, can there be an alternative universe that you are an art major? And so if you can explain decisions in our lives, do we all end up at the destination that we're supposed to be? Or do decisions that we choose go through different portals and end up in different locations? I'm really trying to understand this because, I've thought back about my life or friends' lives where, it could be on both sides. If you make a decision and it turned out to be good and you look back and go, wow, if that decision wasn't made, it could have been really bad. Or on the other side, I should have taken that job offer. I should have moved to the city, or I should have done this, or, I should have gone to this school. Talk to us about what that means in physics, an alternate universe, and then also what are those decision portals?
Okay. So the way that one could look at this, and I'm trying to think of the right way to say it that so I don't confuse myself. One way to look at it is that for every decision that one makes and every decision that anyone makes, the reality that you perceive has changed forever. And many ways that people try to visualize this are decision trees. Like if I made this decision, I could go to this way or that way. But part of that isn't entirely true because not all of the decisions that you make are entirely isolated. In fact, no decision that you make is entirely isolated. There are influences that are always shaping what the decision you think you're making is and what the reality ends up being. So let me give you a case in point. Let's say there's someone standing right beside me and I make the decision to raise my arm. Okay. As I'm conceiving, oh, okay, I'm making the decision to raise my arm. At any one point, someone could have grabbed my arm and made a decision that influences what I end up doing. Like the actual reality of what happens. Is my arm raised or not? And so the decisions that you make give forth, and the decisions everything else makes, gives forth the reality that we end up perceiving with the information that we capture. Whether that means that if I had made a different decision, instead of raising my arm, lowering my arm, that somehow if I could go back in time, I could pursue another reality, and hence the concept of multiple realities. That I'm not I'm not entirely sure that the laws of physics as we know them allow that to happen. However, about realities, there is something that does that people often talk about that is a reality, which is time travel, trying to understand one's position with respect to time. Is that possible? And so there are
Let's break down the time travel. So
yeah, because
it's
that's actually interesting. That's a really interesting topic. Whether
if
time travel is possible.
if someone can create this or crack this, they'll be the next richest person in the world. Everybody wants to go back and make that better decision. But from my research, and of course, I want to hear your expertise on this, time travel is impossible. And so I'll give you an example where if we get in a craft and we head out into space and we get to close to speed of light,
Huh?
and we go across the galaxy, obviously that's going to bring down the duration of us leaving to our destination if we get to close to speed of light. But what that does is it speeds up time on Earth. So we can make a journey across the galaxy at close to speed of light, but we can't come back and still be in the same time period. Wouldn't it be multiple hundreds of thousands or millions of years have gone by because of that? And so can time travel exist even if we get close to the speed of light backwards?
So you like what you just said was it was almost exactly what I was going to say, but arguing the opposite thing, that time travel actually is possible when one perceives time travel with different people going at different velocities. And this concept, this phenomena is called time dilation, that the perception of time, ticking away of time, the process of time depends on the observer and how rapidly that observer is moving with respect to another observer, or another, the technical term is frame of reference.
To
And so
Earth
to
being the
use
frame
your,
of reference and us in the craft, right?
yeah, let's
Okay.
use Earth as a frame of reference.
Okay.
So people sitting on Earth, la, 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 la. And one travels, as you said, near the speed of light, maybe 9/10 the speed of light. So almost the speed of light. And they don't actually go particularly far. They just traverse the width of the circumference of Earth's orbit around the sun. They just go back and forth, to one side of that orbit to the other. And the person who's moving at 9/10 the speed of light in their little vessel can have a watch or a clock, an atomic clock, the most accurate clock imaginable that has no, you know,
No delays.
errors associated, and no delays, no errors. Well, tick, 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 tick through time as if 5 days goes by, but they're moving really fast. The time dilation is that the person who is sitting on Earth in the Earth frame of reference, when that person goes out and goes really, really quickly, their perception is that, well, they're gone a long time. And so their tick, 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 tick doesn't have the same tick perception as the person who's moving really quickly.
And is that
And
because
so
of the distance between them or just because of the velocity of
it's
speed?
because of the velocity. It's because of the velocity. The velocity of the person sitting on Earth with respect to Earth is zero because they're moving together. But the velocity of the person in the aircraft going with respect to the person on Earth is very different. And Einstein was one of the first people to identify that there is this difference in perception of time between those that are stationary in the frame of reference of the Earth, as our example puts it, and the person that's moving really, really quickly. And so here's the time travel. The time travel is the fact that the person who is traveling fast senses when they finally come back home to Earth after what they think is just 5 days has actually accelerated hundreds of years into the future. That's hundreds and hundreds of years in the future. So they are moving, they are jumping, they are quantum leaping, if to have a shout out to the 80s television show, forward in time. Right. But not backward, not backward in time. Now, there have been, to get to your original point, going backward in time, there have been a number of theories that have been proposed about possible ways to go backward in time. Things like tachyons, which are nearly, if I think they're massless, but Chris, if you can look that up, I'm pretty sure they're massless particles that travel extremely quickly. The idea of wormholes that we talked about offline, the idea that wormholes might be able to bring you not only to different spatial locations within the universe, but also might traverse in reverse this concept of the forward motion of time.
So
There are
tachyons,
also,
so faster than light
faster
particles.
than light
So
particles
is it okay? Explain that, because I thought nothing can move faster than light particles.
and light. Yeah. And so part of that gets into the fact that light is a manifestation of electromagnetic fields that persist throughout the universe that has different degrees of amplitude. The idea around tachyons, as you can see, is that the particle, a tachyon, not only has no mass, it has what's called imaginary
Imaginary
mass.
mass. Meaning,
It means that the mass is essentially negative. Not negative mass per se, but it's this is getting now into the math of physics. But it has mass such that Einstein's laws of general relativity as well as special relativity don't truly hold for them, because those rules of general relativity and special relativity presume that an object, like my mouse here, has not imaginary mass, but real mass, tangible mass. These tachyons were theorized to have something that is
negative.
not something, not just negative, but imaginary, which is like not a real value. Getting into what imaginary numbers and imaginary mass mean may derail our
What?
light and lovely conversation.
What
So
wasn't there?
there are possibilities sort of try to close the loop. Sorry for the pun. There are possible ways to conceive of and maybe even measure time reversal, meaning going backward in time.
Two thoughts on that. Chris, if
Yeah.
you could help me pull this up. I think there was a research or university, some type of lab that did this study, and they went, their computer, their quantum computing, whatever it may be, went back 1 or 2 seconds in time, which I don't understand that, because is it just their system that goes back in time? What happens to the rest of us, the observers, if you will? And the second part of this question is, if you are 2,000 light years away from Earth, and you have a telescope and you're looking back at Earth, are they seeing 2,000 years ago, or are they seeing us now?
Being us 2,000 years ago. And that question is much easier to explain.
So in
Uh,
2019, researchers from Moscow Institute of Physics and Technology in collaboration, conducted a research study using quantum computer to reverse the flow of time by a fraction of a second. The experiment, published in Nature's Scientific Reports, demonstrated that a quantum computer could be returned to a state it was in a moment earlier. Okay.
okay, I
So
don't know about this study, but I could certainly look into it to understand
that's interesting. Again, what
what they
happens to
mean by the
us?
state.
Okay.
Yeah, what they mean by that state. It might just be, yeah, that one I would have to read and understand it to be able to articulate it to anyone. But that's actually one of the cool things about physics. You can know fundamental stuff about physical phenomena,
Okay.
but there's always something new that happens.
Yeah, this is
So physics is one of those disciplines where, okay, this is what I know right now. But if observations suggest something else, well, okay, this is now what I know. So it's one of those really, I love physics because it trains you to say, okay, this is what I know at this stage. This is the body of the knowledge of the entirety of humanity at this moment. And we are very happy to say we were wrong. And now this is what we know. That's why, Einstein's understanding of relativity trumped what we knew in terms of classical mechanics, Newton's laws of motion. Well, those laws of motions are true unless you go really fast. And we learned how fast you have to go for Newton's laws of motion to no longer make sense or to hold. Back to your point about 2,000 light years away. So
yeah,
it's a cool thing. So the answer is actually partly residing in the thing that you said, being 2,000 light years away. So, a light year is a distance. It's not a time.
right.
It's the distance that light travels in 2,000 years from a stationary frame of reference. So that means you have a flashlight and you turn it on. That light travels outward, and there will be parts in space, even as far away as the screen here, that will not be illuminated when you turn on the flashlight. But after some period of time, light gets to where you are in space, and now you're illuminated. And so after that flashlight's turned on, and that front, call it a wavefront of light, travels outward, either a wavefront or you could think of it as a particle, either one. Wave particle duality, you might have heard of that. 2,000 years later, after you flipped on the switch from your frame of reference, wherever that particle is, wherever that wavefront is, out there in space, that is 2,000 light years away. And so what that observer 2,000 light years away sees is the information at that front of that wavefront, which is the thing that is traveling to them, that first particle. And then 10 seconds later, they'll get the particle that came out of the flashlight 10 seconds after you turned it on. And then 10 seconds later, they'll get the particle that was emitted from your flashlight 20 seconds after you turned on the flashlight. And so that doesn't mean that you are time traveling. It just means that you are seeing whatever got to you. Now, I'm going to give you something that we could look up. So very recently, in the last 2 years, technology is lovely. We in the scientific world have now been able to capture in real time the traversing of light. And so there's been a film that's been circulating through news agencies as well as online that shows light going through a laboratory where you can see where it's dark and you can see the beam of light coming in. They've slowed it down so that you can actually see light traveling. It's one of the most amazing videos because it helps people realize that there is that it?
The
It
MIT
actually
lab.
lets people, yeah, I think the Media Lab did it. That's right, MIT Media Lab. It
Okay.
actually lets you see how fast light actually is and that it's not infinitely fast, that it does have a finite speed that we can count. And in fact, we can measure it and we can see it in a film or in a video.
How does so going forward, how do you commercialize this and what's the application? So my question is, will a startup commercialize time travel? Will a startup commercialize teleportation? Now, if we were 2,000 years ago, we do live in a world of teleportation, meaning 2,000 years ago, it took a day to go 50 miles or 2 days, whatever it may be. Now, we can do that in an hour. So that's a form of teleportation. We get on the Concorde, we can get from LA to London in an hour. That's a form of teleportation relative to 2,000 years ago. Can we get faster? What happens if we get from LA to London 15 minutes and then a minute and then 30 seconds? Can we commercialize quote, teleportation? Can we commercialize time travel?
So, in the context that you described there, I'd say sure, sure. And I'm not being flippant. What I mean is that if one conceives of transportation, as getting something from here to there, now that something might be a human, it could be a message, it could be a photon, it could be just some zero one, some bit. Then I would say that we are in one of the golden ages of, as you said, teleportation.
Mhm.
There are phenomena that are accelerating how quickly humans can go from point A to point B through flight using, less and less uh, resource to do it, to actually propel one from one location to another. To your point, there are lots of aviation startups that exist. Not lots, but there are markedly improving aviation startups that are trying to do this. And the timescales that you talked about, London to New York in an hour, even faster than the Concorde. There are pursuits very much rooted in science, not technology yet, but science, about understanding things like entanglement, how two objects that don't seem to be connected to each other or related to each other somehow have what's called action at a distance, like some engagement with each other over sometimes just a few inches or millimeters, sometimes over kilometers or miles, or even sometimes over hundreds of kilometers and miles. And so, as we are understanding more fully what entanglement means and how it could be manifest, by sure, there's going to be someone that comes up with a brilliant idea on how to turn entanglement, just like people came up with a way to commercialize kerosene or gasoline, turn that into something that is viable for human consumption. And so, how long that's going to take, that I don't know.
And there's
But
limitations, right? Meaning,
certainly, there are limitations under what we consider to be traditional propulsion of how quickly a human body can go from here to there, even under lots of protection without experiencing severe physical trauma
right, like,
and strain.
Chris, what is I think it's like 9 Gs or 10 Gs or something. What is the limit a human body can handle before there's any type of, disruption? Because so you have fighter jet pilots that can withstand whatever is 9 Gs, I'll say. What happens if you remove the gravitational pull around that? I mean, that's another conversation. 4 to 6 Gs causing blackouts in untrained individuals. Trained pilots with specialized gear can handle up to 9 Gs briefly. Briefly. Okay. Split second, non-voluntary. Okay. So there's the limitation unless we can figure out how to reduce the Gs internally in this transport or the
So,
gravitational pull, right?
okay, so here's part of like the balancing everything, right? G's are acceleration, right? The change in velocity over the change in time. How quickly you go from, or how rapidly you go from, say, 50 miles an hour or 50 kilometers an hour to 60 kilometers an hour. That's an acceleration. And the G uses the acceleration due to gravity on the surface of the Earth as a reference point to how much you're accelerating. So the acceleration, that's one part of transport. But the other part of transport is the actual velocity. And so one of the things about this debate of transport is, well, are you concerned about the actual velocity you get to, or are you concerned about the rate of acceleration, the rate at which you get up to that velocity? And what's the danger point? Well, the danger issue is the rate at which you are changing the velocity that you're experiencing, the change in velocity or the change in time. It's not, and we didn't look up, what is the absolute velocity, the max velocity that a human can experience without passing out and
Do we know
disintegrating?
that?
Yeah,
Chris,
let's
can you?
find out. I don't know the answer to that.
Okay, that's interesting because
But the he okay. I said I don't know that, but I dropped in a little physics in there. And so part of the issue is, well, if you're going at a high speed, the things that you have to worry about are other things that aren't going as fast as you are colliding into you. And that collision creates an acceleration moment, right? Because the thing that, you and the thing that are colliding together will decelerate or have a negative acceleration. And so in those cases, that's actually what you're worried about. Not so much the fact that you're going really fast. You're worried about how fast you're going and how fast you will have to change your velocity because of a collision or something else uh, impeding your motion.
So
See?
it's once you're on the train, you're on the train, it doesn't matter, but it's getting up to those speeds is the problem, and then reducing
Making sure
speed
that
to
you
get
don't.
back to
Yeah,
right.
those are the challenges that we are trying to overcome.
So
And so you go ahead.
if
No,
somebody
please go ahead.
solves this problem, then they're really unlocking immediate travel. And this is more not really around the world, but interplanetary, meaning once we get to Mars, once we get to the moon and there's a base and a hotel. I know there's a YC company out there that's taking reservations for a moon hotel. But once we move to that, then we're talking about, 10-hour trips instead of 3 or 6 month trips. If we can solve the velocity issue and then the deceleration issue, I'm trying to think how to solve this in a simplified version, meaning, is it the craft itself or is it internally? Is it the gravity around, meaning, is there an element out there that can reduce this?
So for practical purposes, let's use the mission to Mars as an example. And let's actually not focus on trying to go really, really fast so you can get to Mars in a week rather than 6 months. The issue once you get out into interplanetary space is in many ways the same issue that you have on Earth. Don't get me wrong. Do not, people who are listening to this podcast, do not say I'm a pseudoscientist because I made this statement. What I mean is that the issue is you still have to worry about colliding into things. So every one of us has potentially had the experience of the wind blowing on your face, either because it's a windy day or you stuck your head out of a car that you were in, anything like that. Some of us have had the experience of hang gliding and your head whips back. And that's because you're running into billions upon billions of molecules, air molecules, that are hitting you and you're having these collisions. Well, if you're out in intergalactic space, people say, well, it's empty. It's a vacuum. I'm like, well, it's a vacuum, but it's not empty. There are lots of things bombarding. There are small, tiny particles. There's light of different parts of the electromagnetic spectrum. There's certainly near the surface of the Earth, near being closer to the surface of the Earth than, say, the moon is. There are lots of debris, that man-made debris, as well as intergalactic debris that's floating around that might be the size of a grape, but traveling at 15,000 miles an hour, that little grape becomes quite destructive. So it's always running into other things, ends up being the challenge that we will have going out to, say, Mars. Another challenge truly is to not discount your question, because it's a brilliant question, is, well, how do you get fast enough? How do you acquire energy that has a high enough density that is also lightweight so that you can go out into intergalactic space, consume that energy that will propel you forward toward Mars in the most cost efficient and, in the case of speed, highest velocity and highest acceleration that is possible and sustainable by your craft and the people inside of it. That's a challenge. And I think people, our society, rightly or wrongly, because I'm not getting into the politics of intergalactic space travel, and there are politics associated with that. People, rightly or wrongly, are starting to think, like, what has to go into getting us there? Of course, we can use all the physics that we know about gravity and using the Earth as a slingshot, using the moon as a slingshot mechanism to help propel us out into space. We've done that for gamma ray observatories and the Cassini intergalactic probe and all of these different telescopes that we've sent out into the universe to probe different parts of the universe. So we've used those sciences. Are there other sciences that might be really valuable based on materials that can help us once we get out of the strong attraction of gravity from the Earth to help us propel to places like Mars, Venus, and other galactic partners?
So the physics has limitations, and I love this because every builder, every founder faces limitations at every
Mhm.
single moment of every day. What good founders do is find ways around it, and they really bet the entire house on getting around it. And so let's talk about avoiding that grape that's traveling at 15,000, 50,000 miles an hour. That's catastrophic. Talk to me about wormholes, black holes, what the difference is there. Can we go through wormholes? Can we set them up to avoid those fragments in space or avoid those particles? And black holes, can we make it through a black hole if we get in it? Does the information can it come out the other side if there is another side? So if you can kind of give us a lay of the difference between wormhole, black hole, and does that avoid the catastrophic events that you see in space, rocks, space junk, space asteroids, whatever it may be?
So I'll give you my layperson's understanding of wormholes and black holes. Not so much black holes, but black holes are a fundamental topic in most physics graduate students' training. Wormholes aren't, or at least from being a student myself and teaching science at a few different places. It's not necessarily part of the standard lexicon, but of course, you hear it. So a black hole is uh, a phenomena for which the forces associated with gravity, a gravitational force of attraction, which emanate from, as far as we know, all real matter, not imaginary mass, are such that, and here's one way to describe it, that the mass is so large that not only does its attraction warp space and space time around it, so that if something gets close to this black hole, and close is uh, a spatial distance called the event horizon, that there's absolutely no way that not only something with mass can get away from it, so it will necessarily fall into and collide with this black hole, but other things like light, because of the warping of space time around it, light can't traverse in that space freely, and it gets warped into the region that this black hole resides in. So when this thing is conceived, it really feels like this entity that just has stuff falling into it. Stuff being things like rocks, paper, scissors, things that we can touch, as well as things that are harder for us to conceive of touching, like light, visible light, X-rays, infrared, ultraviolet, all these different forms of light. Now, there are different ways that scientists conceive of what a black hole is, be it just this huge mass of material sitting there and just accreting things. Some conceptions of it involve truly a warping, a warping of what space and time look like in that region, in that part of space. One thinks of it as truly like a flat plane that just gets curled around itself. I won't get too much into that, but the concept of a black hole that has come into more common lexicon is that nothing can get out of its influence. Everything gets sucked in, and everything gets sucked in if it gets too close. And that too close point, using a more physics term, is called the event horizon. The event horizon is the point in space beyond or closer to the black hole for which everything just disappears and goes into the black hole. So black holes are this kind of intergalactic entity thing that for the longest time we thought nothing could come out of it. There was all light, all matter, everything just went into it until we found out that the black holes have things called jets associated with them. And those are special axial meaning they're along a certain axis, propelling of material, light and other material out from the black hole. Now, the underlying physics of that, I have to admit, I don't know. I did at one point in my life because it was part of my training. It wasn't my discipline, so I've forgotten it. Is what it is. I perhaps am oversharing the fact that I don't remember all of the underlying physics of every single discipline in physics. Most
Yeah,
physicists
who
that I
could?
know would never, no, but most physicists I know would never admit that at all. Like they're like, I know everything, and they would just come up with some answer. I admit when I have no idea. But that's a black hole. A wormhole is a different take on the fabric of space and time. A wormhole is a perception that space and time and the fabric, like we call it fabric, it's a euphemism, but people believe that it could be true that the things around us, we're actually moving through fabric, a fabric of phenomena called space and time. Space being, X, Y, Z, and time being this fourth dimension, if you will, that precedes and before us. What physicists believe is that this concept of there being just three dimensions, everyone's kind of seen this kind of three dimensions, up, this way, and this way, is that there are other dimensions that, for whatever reason, our brains, our notions cannot perceive. And there could be four dimensions, five, six, seven, 17. I remember from graduate school a conjecture of 17 dimensions that are accessible.
Can we
But for
sense them? We
most
can't
of it,
see them, but we can sense
well,
them.
most of us, we can only sense three. I'm going up and down, forward and backward, and left and right. And there's other ways to think about that, forward and backward, spinning around this way and spinning around this way. For pilots out there that you understand uh, what I'm talking about. There are different coordinate systems. That's actually the mathematical term. Radial, cylindrical coordinates are. So there might be other dimensions beyond up, right, down, left, forward, backward that help, if you think about it, help conceive of, well, maybe I can get from here to here, not by using three dimensions, but by using the fourth and fifth dimension that gets me there in a shorter distance. Because in fact, I'm not traveling through these three dimensions. I'm actually traveling through the two other dimensions that are to our notion are in fact side by side in dimension 4 and dimension 5, these 2 points. And so that wormhole allows you to go from here to here through dimensions that in fact we can't perceive with our eyes at this stage. And so it's a different way of thinking about transportation and movement if you think about additional dimensions. Okay, now here's a way to think about it. I'm going to use my phone as a way to think about it. Okay. Tell me how you would go from this corner to this corner by using three dimensions. Well, I could go here and come around and go up here and then get to that corner. That's using three dimensions, right? So far, so good. Let's now say that you live in a world where there are only two dimensions, kind of like what you see on your computer screen or your cell phone screen. Okay, well, I can't go this way now. Okay, I got there in two dimensions, right? Up, down, left, right. Now let's try to get there using only one dimension. Can't go this way, can't go this way. Well, the easy way is that way. And so if you live in two dimensions, you can't conceive of going this way. It's not possible. It's impossible. There's no perception of going this way. You can only go this way or that way. And so this concept of there being other dimensions, fourth, fifth, sixth, seventh dimension, is kind of like living in two dimensions and conceiving of there being a third dimension. It's impossible. It's not possible to think of a third dimension. And so if you use that analogy as a way to think about wormholes, wormholes could be wholly conceivable. They could be all over the place. But the way that we are grounded right now, we just can't conceive of dimension number 4. We can't conceive of dimension number 5, even though it actually helps explain some physical phenomena that physicists have observed and have theorized, that there are fourth and fifth and sixth and 17th dimensions. It's just that we haven't, at a macroscopic scale, meaning a scale that you and I can see and easily perceive, we haven't observed them macroscopically yet. There is some evidence, and this is something we can look up, of the perception of these other dimensions at on a subatomic scale, including truly subatomic scales where we're looking at the nature of what makes up what's called a nucleon, which is a proton or a neutron. And so I fully am willing to believe that there are additional dimensions beyond the three that we can see. We just haven't observed them at a macroscopic scale.
So I want to get to the third, fourth, fifth. What are these? Can we create these? Are they dreams? If you can explain or give an example of what is classified as a dream. A dream could be another dimension. You feel it. You're going through it. You're living through it. So what is that? Can that be the fifth or ninth or the 18th dimension? And how can we recreate that? Can we create a wormhole?
So dreams are interesting in that they, as far as I know, are the manifestation of the collection of neurons that we call and nerve groups that we call our brain. And there's a lot of biological sciences that suggest that humans are not the only living creatures that dream. Other higher levels of life that have deep rooted collections of neurons, i.e., brains or brain stems, have dreams. Now, whether it's solely a product of that collection of neurons or whether there's something else that's going on, that would be lovely to know for me, because I don't know. It would be amazing. It would also be amazing to learn whether the senses that we have, our perception of our reality, and I truly mean that, using all the senses that we have, the sight, smell, taste, touch, hearing, as well as other senses that there's been evidence that there are other ways to sense things around you that don't correspond explicitly to sight or sound,
Right,
but some
vibration,
combination. Yeah,
intuition, whatever that is. Okay.
exactly. Again, based on collection of neurons trying to capture information, signals that are being sent toward it. That actually could be related to the presence of other things like wormholes. The fact that, my analogy of a two-dimensional space not having any concept that you can move in a third dimension because you can't perceive it. You see only this flat surface. There's no information that it can understand. Living in a two-dimensional space, that information coming from a third dimension. This is not possible. And so if you look purely from a physics, not any other way, from a purely physics from phenomenological view, there could be a fourth dimension from which we are getting information that in our three-dimensional reality, we just can't perceive of that signal, be it electromagnetic waves, be it particles, actual matter, what have you, coming from that fourth dimension. And so I fully, as a scientist, I fully accept that as a possibility because I live my life based on what we know as society now. And if there's enough evidence to suggest something else, I'm more than willing to accept that new information. That actually is one of the ways. So I'm going to jump a little bit. This is actually one of the ways that people who I know who are scientists of all different persuasions of science, but who also are deeply religious, reconcile this concept of this. Is one of the ways. There are lots of ways you can do this, and that I've seen people do this, reconcile the existence of God or a power greater than themselves. I am 100% comfortable with people coming with those types of conclusions based on a scientific approach because again, I'm open to people rationalizing based on their own sense of not only what they know, but their own sense of self and their existence to something that I may disagree with. That's actually part of being a scientist. There are people who have rationalized that the Earth is flat. And then there have been people who have rationalized that and then given copious evidence that the Earth is not flat, not only through observation, but through other types of phenomena. And they've changed their mind. There are others that have been given the same phenomena, the same data, and have not changed their mind. And I'm like, okay, that's like I'm not bothered by that. I might say, I don't know if I understand why they think that, but to each their own.
So there is something about that where if somebody enters a room, you can feel their presence, whether they're rich, powerful, good looking or not. It doesn't really matter. You can feel the energy. It's almost that intuition. Is this a good person, bad person? From a religious standpoint or not, I'm religious myself. I'm a Christian myself. And so, I've been in situations in my life where I know there's danger, or I know I've heard or listened to my spirit where it says leave. It's time to leave. Something is not right here. And then you find out later that something wasn't right and it was a dangerous situation, or this is not a good person, or this situation I need to get out of, or I'm comfortable here. And so there is something there. From a scientific standpoint, do we know, is this a vibration? Do they talk? Is this energy? Do each one of our cells have a language that's talking to each other and saying, okay, this is good, this is bad, and then giving you your gut feeling? What is your gut telling you? Where does that come from?
That if someone knew that definitively, I'm sure they would not tell anyone and it would make their lives even either through financial gain or just serenity, even knowing how they could have a rich, not monetarily rich, but a rich personally and perhaps meaningful life that they could share with society. I would say that I agree that there are different ways that humans are able to acquire information. Maybe I always reduce it to acquisition of data, that there are lots of ways that information is transferred from one location, from one person, one position in the universe to another. And it's not always obvious how that information gets transferred. It could be through conventional ways that we accept in society, and there might be other ways. This idea, because I've had it too, where I've walked into a room and something, it might have been just all of my normal senses completely collapsed on a sense, like a notion that, hey, something's wrong and I must act on this notion. It might be that another mechanism for detecting signals in your brain, in your body, it's like some combination thereof, induced a reaction in your body or in your mind to say, okay, something's wrong. Or maybe it didn't actually occur upon entering, but you had a sense, you had already made a decision in a different part of your mind that wasn't in your conscious, but might be in your subconscious, that the decisions that you were making up to this point were not good decisions, and that you should consider other decisions after this point. So let's break that down a little bit. So people often say, "Oh, I walked into a room and I started feeling uneasy." That may not have been that uneasy feeling may not have been induced by you walking into the room. Like the room itself did not induce it, or things in the room may not have induced it. What might have induced it is your collection of information finally coming together to tell you that at this moment in time, you probably shouldn't be there. That's just as plausible. And that actually resides on the fact that you, as a human, have collected information and are processing it at all the time, like all the time. And the action, going to our earlier part of our conversation, the action of walking into the room and the decision you made to walk into the room actually is the trigger, not anything that ends up being in the room. Now, people often rationalize that, oh, I didn't know the person was inside, or I didn't know that the situation was going to be bad. My conscious person, my conscious self, had no possible idea that walking into the room, oh, the ceiling was going to collapse. Maybe other parts of you, before walking into the room, got enough information from the surroundings, from the universe, whatever, to say, if I step 2 more feet through this door, something bad's going to happen. And so I only belabor this point by saying sometimes it's the information that we already have that causes people to react a certain way. Sometimes it's the information that we get in an instant, that is, the walking into the room. Sometimes it's information that we collect after we get in the room from sources that we may not be able to perceive immediately or sense immediately.
So can another dimension be experiments that are 1 in a trillion chance? Here in science, we can't replicate this. This is 1 in a trillion. We just can't replicate this. Eventually, can we replicate that? And is that another dimension that we just don't understand?
So the answer to that is maybe. And so the replication of data, that's a whole lecture series. That's a whole
Okay.
podcast series that certainly people who are scientists and engineers, we know that issue well. And they're even the science of science, like the science of doing scientific exploration that involves the idea of replication. One of the things that I think is interesting to think about is, you said a 1 in a trillion chance. What might actually have been the case is that those other 999 billion, 999 million, 999,000, blah, 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 other times, the conditions to get it to happen weren't actually met. In the universe, locally, like you just didn't actually have the same conditions. And so that's why it only happened once.
Interesting. So it
So,
can't be
so I,
replicated.
well, it can. It's just that getting the conditions to be exactly the same is extremely hard. And what I mean by that is the conditions that matter that could cause it to work or to occur or not occur. You just didn't do enough to recreate those exact conditions. And I have that experience in some of my nanoscience work where I thought I was replicating the same chemicals, the same temperature, the same environmental conditions. And then after the experiment, lo and behold, I found out that one of the chemicals was just slightly off, and it changed everything else. And so doing things exactly the same way, that matters. Sometimes you can do things differently, and those differences don't matter in the result. But identifying what differences do matter in the result, that I think is where one should first explore a 1 in a lifetime or 1 in a million or 1 in a trillion phenomena before saying it's potentially a new dimension. But hopefully you heard what I said. What I said does not discount the presence of another dimension being that one thing that wasn't the same. It actually accounts for that possibility. It sounds like a cop out, but in fact, that goes back to training, like thinking about what are the conditions that allow us to have something happen, and what are all the parameters that matter in that thing happening, and what are all the parameters that are inconsequential or don't matter at all. What of those that do matter didn't happen again or wasn't present again? That might be the reason why you didn't see something once again.
Interesting. Okay. So bringing it back to, we've covered a lot of limitations that physics present, startups trying to blow past that, startups trying to get beyond that. Why does a physicist go to Wharton? Why does James get his MBA? How does this help a physicist? What does this create in your career? Was it just something you were seeking? If you can kind of marry the two and apply it to startups, apply it to being an advisor, a board member, how is it applicable?
I've been very fortunate in my life, personal and professional. So let me start off with that. I am extremely fortunate to be where I am. And I think, I've made lots of great decisions and I've made lots of bad decisions. And understanding that and thinking about that is part of, and realizing, maybe that's even more important, realizing that I am the product of decisions that I've made. I can attribute my physics training to think about my life in that way. So that for me is a baseline, is like a fundamental to understand the decisions I made. Just like that kind of thought. Okay, why did I apply to work? So one of the reasons was that I had gone through being a scientist and developing technologies that I thought I could patent. I had gone through working at a government laboratory helping scientists develop their nanotechnologies and energy related science, and working with companies often to help them pursue technological goals and technological interests that ultimately could be turned into commercial products. After that, I worked for a well known consumer product testing and advocacy organization that interestingly is cited often at Wharton, is trying to work with not only consumers, but corporations and other stakeholders to ensure that consumer products and consumer goods and services are as good as they could possibly be for consumers. All of that, all of those endeavors involved business and involved companies and involved commerce in some way, in some view, in some slice, in some aspect. And there were many times when I was sitting across from a CEO or a chief technical officer more frequently. And when we were talking about the science or technology, no problem, easy peasy. But when we were talking about the business of their companies, it happened too frequently. I'm not saying half the time, but it happened more frequently that I didn't understand what they were saying. I didn't understand, like here in my gut, intuition, and in the little gray cells. I didn't get it. And so I rationalized that if I wanted to be better at being a public scientist, I see myself at this stage of my life as a public scientist, helping society have a better understanding, better disposition, a better relationship with science. That I had to have a better understanding of how business and business people thought. And so that compulsion led me to apply to business school to, at least in part, have a better understanding of how business people think, or at least where they learned how to think as a business person. There were other reasons, as you said, participating on boards of startups and technological spaces to make sure that I had the tools at hand to help them with strategy, with business practice, etc. Those were the main compulsions. To say one more thing, I've had some people that I've interacted with, really no one at Wharton, but people that I've interacted in my life who I've talked to very casually about the concept of business school. This is usually typically before I went to business school. Well, like why? Like why do you need business? Like as a practice? Maybe you're just getting another degree. Like maybe you're a degree hound. Like no, please. No, it's being able to look at yourself in the mirror and say that I'm trying to continuously improve and continuously add to who I am and how I engage with my environment, engage with society. Hopefully, I never end that. Hopefully, I never end that pursuit. So it's not collecting acronyms at the beginning and at the end of your name. It's trying to go through, and it's not even a reinvention. It's trying to ensure that who you are upon waking up is better than who you were when you went to sleep.
I think you touched on a really good point of sitting across from a CEO or an ops person. What are they talking about? And bridging the gap between physics and commercialization. I mean, this is really what the point of this podcast is talking to folks like you that are experts in the field. And I want to understand, the audience wants to understand the limitations, because again, founders push those limits to the max. And it doesn't matter if you're a Steve Jobs founder where it has to be perfect, or just Elon founder that's just speed and get things done and will kind of assemble the kite on the way down. Founders are curious and push the limits. And I believe somebody out there can use your expertise and that extra language that you speak of ops or cap tables or cap raising is really value add to yourself, but also to society if you want to be public facing. Like you said earlier, you mentioned STEM. And I think this is really important of how do you get individuals in elementary school, middle school, high school, focused on STEM, interested in STEM, if they don't have the parents to guide them, if they don't have the surroundings to guide them. It's really important that we're having these conversations, and maybe a clip of this conversation will reach their teacher and their teacher can spot an interest that they have in math or whatever it may be. And so that's really important for me as well to really try to reach out and have these conversations so that they encompass the younger generation to do this, because in 100 years we're going to have a different set of startups and physics, and maybe they're at a starting point of the moon or Mars versus starting point of Earth. And it's super important to have the next generation interested. So thank you for that. I
And
really appreciate that.
literate.
And
So
literate.
for me, like when I talk about STEM, it's literacy, being a citizen of this planet and maybe in the future other planets. Having the literacy associated with all of the things that make you a citizen of the planet. Now, I'm not demanding, I'm not one of these shout it on high and wag my finger that everyone needs to be a STEM professional or even like science and engineering. I'm not that. But I'm as much of a proponent of someone being a STEM professional as they would be being an English professional or a language professional or a social work professional or any other discipline, because I think A and others need to have literacy in those areas too, particularly if they affect the environment that you live in, the community, the locale, your professional space. Having that fluency and literacy is very important. It's served me well in my life. One way to call it, and some people use this as a derogatory term, is that I'm a generalist, one that has been able to take training in one discipline, one area, and find connections, ways to relate to others in other disciplines. That has served me well. I certainly have very strong foundational understanding and training in physics, but arguably I have strong foundational training and understanding in other disciplines too that have branched out from my experiences that, again, come back to, I guess, curiosity and interest and a love for learning.
I appreciate that. James, well, thank you. I really appreciate your time. This was a really fun conversation. So thank you. And thanks to everybody listening.
Legal disclaimer: the views and opinions and statements expressed in this podcast are those of individual speakers and do not reflect the views of their organizations or the producer. This content is for informational and entertainment purposes only and should not be construed as medical, financial, legal, tax, or investment advice. You should always consult appropriate professionals before making decisions related to your health, finances, business, or legal matters. References to any companies or services do not constitute endorsements. The producer and participants disclaim all liability for actions taken based on this content and make no representations as to its accuracy or completeness.